For more than half a century, humanity has followed one simple path toward more powerful computers. Generation after generation, smaller transistors allowed us to place more computing power into smaller spaces. The result is extraordinary. Billions of tiny switches working together to perform calculations at unimaginable. What once required an entire room can now fit inside a device that rests in the palm of your hand. But every step downward makes the engineering problem harder. More transistors can mean more computation, but they can also create more heat, more complexity, and greater demands on energy. At these scales, moving information across the chip can become almost as important as calculating the information itself. So engineers are exploring new architectures, new manufacturing techniques, and something even more fundamental: new materials. Silicon has powered the digital revolution for decades, but the future may not depend on silicon alone, and that is where the next technological revolution may begin. Not with a new computer, but with a new material. Imagine a future processor containing 1 trillion transistors, not as science fiction, but as an engineering target shaped by. One of the most famous candidates is a material made from something remarkably ordinary, carbon. But if we keep shrinking the transistor, eventually we approach a world where classical engineering meets the strange behavior of matter itself. Graphene is only 1 atom thick, yet it possesses extraordinary electrical, mechanical, and thermal properties. At the smallest scales, quantum mechanics is no longer an abstract theory. It becomes part of the engineering problem. Electricity can move through graphene with remarkable efficiency, making it an extraordinary candidate for future electronics. That is why the future of computing may depend on technologies that do not simply make the transistor smaller, but extraordinary electrical performance does not automatically make a perfect computer transistor. One of the most radical alternatives comes from quantum computing. For digital logic, a transistor needs to switch between states reliably, and graphene's natural electronic structure makes that difficult. Quantum computers do not simply use smaller transistors. They use physical systems whose behavior follows the rule of quantum mechanics. So scientists began searching for other materials that could combine atomic thinness with better control. A classical bit is designed to represent 0 or 1. A qubit uses quantum states that can be manipulated in fundamentally different ways. Superposition gives quantum algorithms a mathematical space that is very different from ordinary binary computation.
Entanglement can create correlations between quantum systems that have no simple classical equivalent.
But quantum computing comes with its own extraordinary engineering challenges. Quantum states are fragile, and keeping them useful requires extraordinary levels of control. Quantum error correction attempts to protect useful information from the noise that naturally affects quantum systems. So which machine is more powerful? The answer depends entirely on the problem. Quantum computers are not replacements for ordinary computers. They are designed for problems where quantum algorithms can provide an advantage. For most of the digital world, classical processors will remain essential for a very long time. The more realistic future may not be quantum versus classical computing, but quantum working alongside classical machines. Each type of processor could eventually perform the tasks it handles best. AI is already reshaping computing, and quantum processors may eventually become another specialized tool in that ecosystem. One potential application is chemistry, where simulating molecules can become extraordinarily difficult for classical computers. Quantum computing could eventually help researchers explore molecular behavior. This is difficult to model efficiently with conventional machines. Another possibility is scientific simulation, from materials science to chemistry, and potentially parts of climate modeling. Better simulations could help humanity design materials with properties we cannot easily discover through trial and error alone.
Optimization is another field where researchers are investigating whether quantum methods could eventually offer useful advantages.
And then there is security, where quantum computing could eventually change both the threats and the defenses surrounding digital information.
Some widely used cryptographic methods could become vulnerable to sufficiently capable. That is why the transition to post-quantum cryptography has become an important part of preparing for the future. But even in fields where quantum computing may eventually matter, classical infrastructure will remain. A quantum computer can be incredibly powerful for the right task, yet the machine around the processor can be enormous and complex. The challenge is not simply creating qubits. It is controlling them accurately enough to perform useful computations. Progress is measured not only by the number of qubits, but by how reliably those qubits can participate in useful computation. In quantum computing, quality can matter as much as quantity.
And this brings us back to the original question. Will the future belong to trillions of transistors or to qubits? The tempting answer is to choose one.
But the most plausible future may be more complicated and much more interesting.
Instead of one technology replacing another, computing may become a hierarchy of specialized machines. The winning computer may be the one that knows which kind of processor should solve each problem. By the middle of the century, computing may no longer be a single machine. It may be an invisible infrastructure woven into civilization. Cars, robots, factories, hospitals, and cities could all depend on different layers of specialized computation. Medicine could benefit from faster simulation, better optimization, and more powerful artificial intelligence.
And beyond Earth, more powerful computation could help us design missions to environments where mistakes are measured in years.
The computers of the future may become as important to exploration as the rockets that carry them. But there is another question hiding beneath the race for computing power: energy. More computation is valuable only if humanity can afford the energy required to run it. That is why the future of computing is not simply about speed. It is also about efficiency. The most important processor of the future may not be the one that performs the most calculations, but the one that performs useful calculations with the least. Another revolution is happening beyond the transistor itself. Engineers are learning how to combine many specialized components. The computer of tomorrow may be less like a single chip, and more like an entire computing ecosystem compressed. Even the way computers move information may change, with light increasingly becoming part of the communication architecture. The next breakthrough may therefore come not from one technology, but from the way several technologies are combined. The future is unlikely to be a clean victory for one architecture. Instead, the future may reward the systems that work together. The race toward better computing is already a race across many scientific disciplines. Physics, materials science, engineering, computer science, and artificial intelligence are converging into one technology. At the deepest level, every digital revolution begins with matter behaving in ways engineers can control.
The future of computing, therefore, begins at a scale far smaller than the computer itself.
Turning a laboratory breakthrough into billions of reliable devices is often harder than discovering the idea itself. The same is true for quantum computing. A laboratory demonstration is only the beginning of the engineering journey. Classical computing has a massive advantage: decades of industrial infrastructure and manufacturing experience. Silicon is not merely a material.
It is the foundation of an enormous global technological ecosystem. Quantum computing must build much of its ecosystem, while classical computing already dominates the world. Hardware alone cannot transform computing. New machines also require new algorithms, software, and ways of thinking.
The next computing revolution will also require a generation of scientists and engineers capable of working across these.
The boundaries between computing disciplines are beginning to disappear. In the future, computation may become so deeply embedded in society that we stop noticing it. Factories could become computational organisms, continuously optimizing how materials, machines, and energy move. More powerful computing could also help coordinate increasingly complex energy systems. The ultimate goal is not to build powerful computers for their own sake, but to use computation to understand and improve the world. Perhaps the most important computer of the future will be the one that helps us understand Earth itself. Whether quantum computing can transform these simulations remains an open scientific question, but the possibility is powerful enough to. The future of computing will therefore be measured not only by how many calculations we can perform, but by what those calculations. By the middle of the century, the computer may no longer look like the machine we recognize today. It may be a network of different machines, each designed for a different layer of the problem. The processor itself could become a miniature ecosystem, combining multiple technologies instead of relying on one. Quantum computing may become something like a specialized accelerator, called upon only when its unique strengths are useful. For ordinary people, the quantum revolution may happen quietly, hidden behind familiar screens and devices. We may never own a quantum computer. We may simply use services powered by one. And just as cloud computing made massive classical machines accessible from anywhere, future quantum resources could become part of a. The real winner may not be a processor at all. It may be the architecture that connects them. Because computing is no longer just a tool. It is becoming part of the infrastructure of civilization. From atoms to algorithms, the journey of computing is ultimately a story about how humanity learns to control matter and. So, will trillion-transistor processors dominate the future? Or will quantum computers take their place? The answer may be neither, and that may be the most important insight of all. The computer that dominates the future may be a hybrid machine, using classical and quantum technologies together. The most powerful system may be the one capable of choosing the right architecture for every problem. That future would not be defined by one technology replacing another, but by technologies becoming increasingly specialized. And if that future arrives, the most important breakthrough may not be the fastest computer ever built, but it may be the moment when we learn to combine the strengths of many different kinds of computation. Because the future of computing is ultimately not about machines. It is about what humanity chooses to do with the power they give us. The race between transistors and qubits may never have a single winner. The future may belong to the civilization that learns how to. A new computational architecture for civilization itself. What kind of future will that power create? Future Earth. What will